Okay, welcome to the second week of the Optimization for Machine Learning course. Today we're going to dive in and study the main algorithm of interest in this course, which is gradient descent. You probably heard about this already, but today we really will see how we can get convergence rates for this important algorithm. Before we go there, just a little reminder. So don't forget to check out the materials, which we always update on our GitHub. So it's optml course, where you always find a new exercise sheet is always there on Monday, and the solutions are always there on Friday. So make sure you look at the exercises before you go to the classes on Friday. Okay, so gradient descent, what is happening here and what even is the goal of all of this? So the goal is very general, so we just want to optimize a function. That's what optimization is. We want to minimize function f, so we want to go somewhere where the value is almost the optimum value, which is f of x star. There might be several and so on. Sometimes there is such a global minimum, sometimes there is not. So, but our goal is really to find a candidate x, which is not perfect maybe, but good. And what good means is that the value is very close to the best value you can have. So, and that's exactly what is written here. So you found an x, which is your candidate, and you say that it's epsilon close to the best value you can get. So this is kind of your target accuracy you want to achieve, or your so in a machine learning setting, this would be like the training loss, which you optimize, and you want to bring that epsilon close to the true optimum if you can. So this is the goal. This has nothing to do with algorithms yet, but now how we can achieve this goal is by certain algorithms. So sometimes you can find the solution in closed form, sometimes you have an iterative algorithm and so on. And here we're really interested in this most basic iterative algorithm you can have, which is the gradient descent algorithm. How does it work? You know this already. So you take, you are currently at the point x, xt. What you do is you're going to move towards the negative gradient with a certain step size. So that is the algorithm, and the gradient is taken, of course, at your current position. So gradient we already seen last week what it is exactly, and gamma here is a step size which tells you how far do you want to move in that direction. Okay, that is the basic idea. So step size is gamma, some small value bigger than 0, and then t is our counter for time. So just time t increases in every step. You start at t equals 0, and then you see where that brings you. And then you repeat the step many times. So far so good. And now the question is, what does this do? So here's a very simple two-dimensional example what gradient descent would do on a quadratic function. So the function value here is indicated on the bottom. It just takes, it has only two variables in this example, two-dimensional variable. And what we do is we start here at 0 with our procedure. It's our first point, so this would be x at time 0. So the notation might be a bit confusing. So then you compute the gradient here. So this vector here might be the negative gradient, because gradient brings you uphill and we want to go downhill on our objective function f. So here's minus the gradient at my current position, which is called x0, and that brings me somewhere there, and I have a step size which then scales this step to bring me more or less far in that direction. Gets me to the next iterate, which is the point at time 1, and then I repeat time 2, time 3, and so on. It will never really bring me to the perfect optimum, so that here will be my optimum here, which happens to be unique because this is a strongly convex function. also strictly convex functions as well. And we're not getting there exactly, but we're gonna get there very, very closely. We are converging to the true optimum, which is very nice. This is for this particular step size of 0.1. Of course, you can use different step sizes, and this is not perfect here. We will see in the future. So how to set our step size for which type of function, and when this algorithm is faster and slower, depending on the conditions. I hope the intuition is clear, and yeah, very good idea to also implement it yourself, and you will have the opportunity in the nice Python notebook of this week. So you can use this on Google Colab, for example, a very simple notebook where you can play with gradient descent on different cost functions. Okay, but what we want to do here is to analyze how fast it needs to converge, and this is our measure of progress here. So this is the current error. So I'm at xt, right, and I want to go to the something which has a function value close to x star. So I want to bring this quantity down. So can I make this really, really small? So you would like to have this error decrease over time. Time is called t, and here would be f minus f of x star. So we want this to decrease as quickly as possible to go to 0 ideally, but it's maybe not going to be perfect. But we want to analyze how fast this goes in dependence of the time t. So to do so, maybe the first step will sound a bit magic to you, but we will look at the gradient, and we look at how that gradient here relates to your position relative to the optimum. So you're currently at position xt. You want to go to the optimum. We don't know where the optimum is here, right? But we're doing a theoretical analysis, so we can still consider that vector, that quantity. So we want to say something about this quantity. So I have this gradient, I'm at xt, I want to see how I move towards x star or not. This quantity, by the way, is the same quantity you have seen in the optimality condition for a constraint problem, but here it's for a very different purpose. Okay, so if I do, so on here we do nothing special, we just use the definition. We say, what is our gradient? Our gradient actually is identical to the step we have performed. So because the gradient step was, as we said in the algorithm, it's defined, my new point is defined to be the all point minus gamma times gradient. So that means the difference between all the new point is gamma times gradient. And that's what we have done here. So here's the difference between the new and the old point. And I just plugged in that this is gamma times gradient. So that's the definition of the step. So nothing has happened. And now we want to go further. So we want to talk about we will see later why this is going to be useful, but we will see that if we talk about the norms of these quantities instead of the inner products, then that is going to help us for the analysis. So how can we, so this is the inner product, right? It's the transpose of this vector, inner product with this vector. So we don't like that. We would like to have norms there. So how can I relate norms to inner product? And the simplest way to do so is this here. So actually that's very simple. This is just a standard identity of vectors. It's saying that the thing on the right, the difference of two vectors, is the same as here, norm square, minus 2 times the inner product. So that's nothing else than this identity here. So this allows us to take inner products and instead write them as norms. So that's something, of course, we can do. We're going to see later why this is useful. So we take our quantity of interest, on the left side, and now we write it here by plugging in the two v and w variables to be the two vectors we have in our quantity. What that gives me is v squared norm, w squared norm, and w minus v squared norm. So that's what's written here. It's an equality, nothing has happened. I just rewrote my vector, or I rewrote the inner product of my two vectors. Otherwise, all the same. And now, again, I will just use the definition of my gradient to see that, okay, here I actually have the difference of my new iterate xt plus 1 minus the old iterate xt. And that is, again, the gradient times my step size. So gamma times gradient is this, and that actually is a squared norm. Therefore, there will be a gamma square, which cancels with the gamma we had in the denominator here. So that's why now I get gamma times my squared gradient norm here. So this is nice because the gradient is a quantity I have available, and we will see that this is going to be helping us to give our convergence rate. On the right side, nothing has happened. I kept those terms unchanged. Now we are almost done. So now we can sum up over all our steps to see what is the kind of the sum of all these effects that have happened here. Because I claim that the quantity on the left is describing me how much progress I do, and we're going to see in a second why. And this quantity is summed up over all time steps from I start at 0, I do many steps until capital T. Let's see what that gives us. I just say I will do capital T many steps and sum up my quantity, and that's going to result in this expression here. Here nothing interesting has happened. It's just the gradient has been summed up over all iterates. So this is the gradient at your initial point plus the one at the next point. Everywhere, every gradient you encounter, it gets summed up here with the square norm. So these guys will add up to quite a large value in the end. We're going to see that. What about the other terms here? So this is more interesting here. So here we see that everything of these differences to the optimum, that's the quantity we can understand, and which is also of our interest. We want to get closer to the optimum. We see that they all have cancelled out except the very last one at time t and the very first one at time x0. So this is the sum. You see, when for every t there is the term t and t plus 1. There's many of these terms. The nice thing is always the next one from here cancels the previous one from here, from the previous t. So the only two terms which survive of these t times 2 terms, when I sum them up, the only two terms survive is the first one and the last one. So, and this is what we basically call this telescoping sum. Just summing up all these guys and seeing that only the last one and the first one survive. So last iterate, how far am I from the optimum? And the first iterate, how far am I from the optimum? These have a very nice interpretation. That's why we like these terms, and the gradients also have a useful interpretation, as we're going to see. Now I just have to tell you why this whole story even relates to optimization. So why does this quantity here have any interest to us? Why does it tell us that progress, that we make progress in terms of function value here? So that remains to be done, but that is easy, as you're going to see on the next slide. It's just going to be convexity, basically. I mean, what we've done here on this slide is everything is an equality. We have not used any inequalities. We have not used any assumption on the function. So this slide here is completely true even for non-convex functions. But now to relate the progress to the optimum in f of x star, now we need to see, do we need to introduce some assumptions to understand how the yellow terms relate to each other. So that's here. And as I said, so the simplest thing to get the connection is to use convexity, and which definition, so not the geometric one with the line, but we always use the much simpler one which use in optimization, which is the inequality, saying that my function will always lie above its linearization. That's what this inequality does here. So for any xy you want to choose. So for us, we see that we have these terms xt and the optimum. So that's going to be the 2 points for which we want to use this convexity. So we use xt as 1 point, so that's the point at which we take the gradient here. And then we use as y, we use the optimum. That's kind of the unknown point where we would like to know how big is our function value. Okay, if you use the definition of convexity for the 2 points, so you don't need to know anything about the previous slide. It's just for the definition of convexity alone gives you this. So that wherever you are, your difference to the optimal value is upper bounded by gradient times your distance if you are away from the optimum. So that holds for any method. And now when we sum this up over all times, then we get something which is very, very similar to what we had on the previous slide. So that's what we're going to do next. So okay, now we have related the quantity gradients within a product. We have related that to the left side to the difference in function values, which is what we want. So now we just sum up this inequality, because then what we get, if you sum this on the left, that's fine, and if we also build a sum over t on the right side, this sum over t on the right side, that's what we have here in our equation on the previous slide. So that's what we understand how it behaves over the iterations, and now we also have how that behaves during the when we add it up over time. We also know how it relates to the function values. So overall, what we get when we sum up this whole inequality and then use the thing on the previous slide is this. So here's the sum over all function values encountered during our optimization process. And then here is what we have from the previous slide sum up, because that is the sum of the right the right hand side, right? So this thing, and so we have actually 3 terms. Why is there only 2 on the next slide? That's a bit confusing. So the one here is appearing with a negative sign. So the first one is identical. This one we have as well, and then to be honest, there was this other one. So same kind of step size, and then we had the norm of xt minus the optimum, right? So but what we have done is we have just ignored this term because it's negative, right? Or if you want to be precise, you can say it's non-positive. So okay, that's why we now have now is the first time we actually have inequality, and that inequality comes from the convexity, and it also comes from the fact that we have just ignored this second term here. So and now we're done. So because now we have found an upper bound over the average error over all our steps. So that's what the left side is here, right? We're summing up the error at any time, so current time whatever x0 from to the optimum value, and xt, capital T, and so on. So at any time we have some of these errors. You can say, okay, if this is upper bounded, then we are done, because then we can say, okay, also the average value is upper bounded, so there must be some value which is upper bounded. So we will see how to control the right side very soon. but for now, let's just say that is our bound. And on the left side, we see that, okay, this thing is small, the whole sum is small, but it doesn't necessarily tell you that the last iterate is the best one. It's not saying that this is the case. It might be that another iterate is the best one. And then what we also see is that the step size, the gamma, has an interesting effect. So on the first term, the larger step size, the more progress you get. But on the second term, the weaker the bound is, the larger gamma, the weaker the bound here is, the higher it is. And here on the right side, you see that the larger the gamma, actually the better, because there you see that then it matters less, so then you have a smaller bound here. So we have to discuss how we choose our step size and how it's going to influence the rate in the end. Okay, so here is how this whole thing is summarized into one theorem to make this a bit more formal, so what we have done. And now we also bring in some crucial assumptions on our function, because what can we say? So we have just seen that, okay, it's sum of gradient norms, but we don't know anything about our gradient norms. So now that will come in as an assumption. So if the gradient norm of our functions are okay, are bounded, then this rate here will be nice. And that's what's written in this theorem. So, and that's the first assumption here, right? The gradients have bounded in norm. It sounds a bit strange, but it's actually a very natural assumption. This assumption is equivalent to the function f being Lipschitz continuous, which is certainly a very basic and natural assumption. I hope you agree with me that this seems a nice natural class of functions. And that property being Lipschitz continuous, that property is equivalent to being gradient norms being bounded of the same function. On one hand, that's very nice and clear. On the other hand, it also rules out good classes of functions. So for example, here you see that, just a simple squared function, x squared in one variable. That function does not satisfy this property that the gradients are bounded everywhere. Why not? Because the gradient of x squared is just x, and that goes to infinity when x becomes very large or very small. So then in absolute value, the gradient can become arbitrarily large. Anyway, that's to discuss our assumption, and now let's discuss the result. The result is this main convergence theorem here. It's saying that if the function is convex, so that's something we need to assume. We discussed this on the previous slide. It needs to be differentiable so that we have gradients. And we want the global minimum to exist here, which is technical assumption. So this is, it doesn't need to be unique, right? It just needs to be a global minimum, which we here denote as x star. So because then we need to talk about which is this x star point of reference, right? But there can be several minimas, but this theorem holds true for any choice of a global minimum. So, and then come the two a bit more crucial assumptions. So, and these assumptions are going to be the ones which determine our rate, and that there are two of them. The one is the initial distance to the optimum, and the other is that the gradient norms are bounded. So for both this, we have a quantity which describes how much this is the case. So initial distance to the optimum is called capital R, and the gradient norm we say that is always bounded by capital B for any point which you encounter, or any point x here where a function is defined. So if you have that, then you just choose your step size like this. You choose the step size being proportional to R over B. And this is a constant step size because it just needs to be determined by the total number of steps you do. I decided I want to do a big number of 1 million steps. So that's my capital T is 1 million. Then what it tells me, I need to set the step size. And then the result is very nice. The result of the theorem is going to be that the error, actually the average error, is giving me this very nice convergence rate, which is 1 over square root t, and the constant of it is exactly r times v. which is nice because it tells us that both the R is kind of measuring how difficult is our problem. The further from the optimum I start, the harder my problem is. And the gradient norm is the other measure of difficulty of our problem. It's saying that if the gradient norm is very large, I will be a bit slower because my error will be a bit larger. So, but I can compensate for that by just doing more steps, right? You could just have capital T is the number of steps you do, can be arbitrarily large. Just telling you, as depending on how many steps you do, your average error will be of this order of magnitude. So this is the convergence result. And sometimes we also write this as 1 over square root t in the order notation. Sorry, somewhere here. To simplify if you don't care about the constant, but this theorem here is really, it is about understanding how these constants influence the convergence rate, that depending how hard your problem is, that's going to tell us how many steps we're going to need. Because the accuracy is going to be 1 over square root t. Okay, so how do we get this from what we had so far? It's basically for free, we already had it. So the proof is very simple of this. So it's really, we were already finished. So because we had our vanilla analysis result, which was giving exactly the thing on the left. And it just remains, the only thing we do now is we will plug in our assumption on the gradient norm. So we're going to say this is bounded by B, and we're going to say this here is bounded by the initial distance, which we call R. And then we're done. So that gives us our theorem. So if you want to do this formally, then here that's happening. So here is, you have replaced gradient norm upper bounded by B, and then you have replaced the initial distance with R, and that's what we will do here. And then that's what you get here, B square, and you get R square for the initial distance. Otherwise, nothing has happened. But now the main question is how to do our step size. And because the theorem we had was for a very particular step size, and why that step size? So the step size again is the smaller the better here, and the larger the better in this term. So that's why we need to balance these two terms. So how do we do that? So now that we have a better handle on the magnitude of these green terms, we can set our gamma to make this upper bound here the smallest possible. So that's what we want to optimize, right? So that is how we're going to choose our gamma, such that it minimizes this term. So that's just a number. It depends on one variable, so it's very easy to solve it in closed form. You just set the derivative of this term with respect to gamma to 0. That's what you do here. And you obtain the formula for the best possible step size for this right-hand side. And it turns out to be exactly R over B times square root of t, which is exactly what we used in the theorem. So we're done. The theorem follows just by actually dividing this to t, then you have the average error instead of the sum of the errors. So nothing happens on this slide basically except plugging in the assumption into the vanilla analysis. That's nice. So now this finishes our main and first convergence theorem, and it's a very typical rate that we have, how it depends on the number of steps we do, how the error depends on the number of steps we do. And recall again, it's not about the error of the last iterate, but this is about the average. So some iterate will be good, maybe it's not the last one which is the best one, but on average they are good, and so therefore also one of them must be good. And good means that it has function value is this far away from the optimum at most, which is a very small quantity if you do a large number of steps. Great, so we have our first convergence rate, and again it's very important to keep in mind for which function values this holds, right? So which assumptions did we impose on our optimization problem? So this was for Lipschitz and convex functions. And the rate we had was that this many steps, the rate we got was that the error is smaller than this, right? But now, how many steps do I need to get some epsilon small error? How can I do that? And that's also very simple. It's just that, okay, you said, okay, I just want my error to be smaller than epsilon. And how many t's do I need to do to bring that value smaller than epsilon? Just solve it for t, and you see that if t is bigger than 1 over epsilon squared, then the thing you get on the right side is what you get. So that's asking how many steps we need. So to get epsilon accuracy, you need 1 over epsilon squared many steps. That's just a different way of saying the same thing, that if I do t steps, my error is 1 over square root t. The same thing to say that is that to get epsilon error, I need 1 over epsilon square steps. This is our equivalent. You could just solve for t or solve for epsilon. Okay, let's discuss a bit more about what we have obtained in this theorem. So what is really cool is that this rate is independent of the dimension of how many variables we have. That's really the beauty of gradient descent, that you can do this in 2 dimensions, you can do this in 2 million dimensions. It doesn't matter. There is no dimension d which ever appears in anywhere in our convergence rate. So let's look at the theorem again. So no dimension here at all, right? So this is completely free of any dimension. It's might be a bit hidden, right? We do have an assumption that the gradient norm is controlled. That might be slightly harder in a million dimensions than in 2 dimensions, but it's a reasonable assumption because it means that our function is Lipschitz continuous. So that's all it means. And the distance here is also something that's very natural and is dimension independent. So the only quantities we use about the geometry of the problem or about our function f is the how continuous is it, that's a b, and how far our initial point is from the optimum, that's the quantity r, and that's all. There's no other dependence on dimension. And as we said, it holds for the average iterate, and it also holds for the best iterate as you prefer, but not for the last iterate necessarily. Okay, another small thing you can think about is what do we do if you don't know r and b? So that might be an issue. So why is that? Because we need to know both r and b to determine our good step size, to know that we have step size which works for our theorem. So if you don't know r and b, what we can do is some trick to choose them. And for example, the continuity constant, which is the b, can be easily chosen by doing kind of a binary search. Like you can try a value, and if it was too big, you could divide it by 2 and so on until you find a value which works. And you can see in this exercise 15 that yes, this is actually possible, at least for the quantity b. So in practice it's not such a problem, but the step size is something that is very important to tune anyway. So people usually do take the effort to try several values of a step size to find the most performant in practice, right? So, and if you had the theoretical step size here, if you would know perfectly the b and r, then you could also use this one, or otherwise you will have to try several gammas and see which one works best. And you will observe it in terms of looking at your error. You do observe the error, but you might not know if that's the best you can do, so you have to try which one makes you converge faster in decreasing the error. Okay, that's for the first result. Again, continuous, and the result we obtained was 1 over epsilon squared. Many steps are good enough. Now, can we do faster, or what other assumptions could there be on functions such that we can study the convergence of gradient descent? And another very nice and reasonable assumption is when the function is so-called smooth. And that again will be very important to analyze all kinds of machine learning problems. And also this is something which is important even so both the result we've seen so far, being Lipschitz, is a property which can hold even no matter if you're convex or not. And also smoothness is a property which can hold no matter if you're convex or not. So we will see later when you go to non-convex optimization that the tricks and the key tools we learn here will also work for the non-convex world to get slightly weaker results, but still to get some convergence results. Okay, what does it mean to be smooth? So a function is smooth if it doesn't grow faster than quadratic. So if it, or if you want to say it differently, then you would say it's above its linearization, but not too much. So it's not above the linearization plus a quadratic term here. So here you have this smoothness constant L. So we say that the function is smooth with parameter L if for any pair xy the function is below this quadratic. So, and we say that if you want to be very precise, then you say this is smoothness over a set x. So the function is smooth with parameter L over set x if this is the case for any pair x and y. All right, let's visualize this. Maybe that's easier. So I'll get back to the definition in a second. So here is the picture. So you can see that we are at x, right? And we do the usual thing that we consider the linearization. So that's here. So that's the thing given by the gradient, right? We know what convexity means. That we lie above the green line. And then we have smoothness now, which is a different thing. So what smoothness means is that our function is below this parabola. And that parabola is given by, the green line plus the quadratic, which we have defined here. So here you can see this L. If you have a large value L, smoothness with a large value means that there is a parabola which is very steep, so you have kind of more freedom. And if you have a very small L, then that means that you're almost flat. You're very close to the green area. So that would mean a smoothness, a kind of a stronger smoothness value, which means that the L is actually smaller. So keep that in mind when discussing the smoothness. And so here is your F. All right. So F must lie between these guys. That's the definition. Let's see how we can use it, because this is a very useful property. And let's see if we also have this assumption on our function, then do we have an even faster gradient descent convergence maybe? So that's what we're going to find out. But first, let's discuss the property a little bit more so that we're sure what it means. So it's not hard for you to show that quadratic functions are smooth. So a small exercise which I can recommend. It's in the lecture notes, and also you will have the solutions later. And so that you should do to figure out the definition. And then another one is that you can, so that's what's in the lemma here, to say that, okay, you can combine smooth functions and the combination is still smooth. So one has to be a bit careful what kind of combinations we can do. It's a bit similar as with convexity was also. It was definitely no problem if we had functions where we took a linear combination of them, then the property was preserved. And that is also the case here. If you have a bunch of functions, 1 to fm, they're smooth with different parameters, then you combine them linearly with some different weights, and then you have that the resulting function, the sum of, or the combination of the original ones, is still smooth, and the resulting smoothness parameter is the same kind of weighted sum of the LIs. That's very easy to check by just doing the definition. Another one which can recommend having a look is to say what happens if I do linear functions. So, and then I do composition. So So I have a function f which is smooth, and I combine it or form the composition of f with a affine or linear function g. What happens then? So here is the result. The function f applied after this linear function g is still smooth, but not with L alone anymore. But now it will also depend on the spectral norm of the matrix squared. So again, this is a very good exercise for you to see, okay, if you can, what happens here is that we reparameterize our parameter of the original f. Like the original f was maybe depending on a variable y, but now that variable y gets reparameterized to be ax plus b, right? So it gets reparameterization of the input space, and so you can choose different coordinates, which you of course can do. And but if you do that, the sensitivity of your f depending on the new parameter x might be different, but it's very nicely controlled. You can just say that the spectral norm, which we had last week, which actually defines how bad can the transformed value ax change depending on x. In the worst case, right, that's the principal direction of this linear matrix. How far can that change? And that's multiplied by your original smoothness constant, and you will have still smoothness of the combined function f applied after g. That's also a nice thing to do. So we have this way we can already have quite a lot of smooth functions, and one which is nice is quadratic functions, of course, because that's actually something we were not able to analyze before, remember, because we assumed a global continuity, Lipschitz continuous, which is not the case for quadratics, but smoothness here is the case for quadratics. So what's the relationship of all of this to bounded gradients and bounded norms and so on? So what we already had in the first analysis was that bounded gradients is the same as f being Lipschitz continuous. So that we already saw on our first proof. And now we have a different property, that's smoothness, and it turns out that that also has a very nice and easy relationship to gradients. So, and that is namely that now it's equivalent to my gradients being Lipschitz continuous. So that is another, actually what we use in optimization is more the two things on the right side, which are simpler for us to handle. These are the properties on f. But they are equivalent to the definitions we have seen, which is nice. So you can kind of think of this is kind of the first order assumption. So you have if you're continuous, that means okay, you have an assumption that gradients are bounded, and now if you're smooth, then that's different. So then what that means is that your gradients are Lipschitz. So you want to say they change not quickly, and in the first case you want to say they are bounded. So that's kind of the higher order and assumption on my function. Okay, so why is this the same? So that's just the proof of what we just said, that the yellow property here is formalized in a lemma. So we proved this for the convex case because then it's to be precise, that's what will be equivalent here. If we're convex, then this would be perfectly fitting because we only allowed our function to be below the quadratic. If you want to do this for non-convex, you can do as well, but then you need to say that smooth means you're both below a quadratic and also above the minus the quadratic. But that's not what we had, so the definition you have seen here, you will get this equivalence here. If your function is convex, then you get it, which is very simple to go both ways. And that's exactly what it means to be Lipschitz continuous gradients. So you can see that the objects change slowly depending on the change in x and y. That's what this means. And this lemma is also proven in the nice slides of Boyd and Vandenberg, if you want to have a look. Okay, for now it's good to just remember this property, and then I think we are good to go to now this will be the main tools which we need to now prove a rate for smooth functions, whereas on the previous half an hour we have proven the rate for Lipschitz functions, which is kind of a different assumption. How can we analyze progress when we optimize on smooth functions? And one very nice result here is, which is even better than what we had in the continuous case, is this one here. And what it tells you is that if you have smoothness property, then you can use a very simple step size, which is just given by the smoothness alone, no matter how many steps you do. So this is just a constant step size. And what it tells you is that you will make a strict progress in your function value if you do this. So why is this nice? It's because so it means your new value is strictly better than the old value. By how much? So this is the improvement. So the gradient at your current position xt is always, it's not zero, right? Otherwise you would already be at optimality, because here we do an unconstrained optimization problem. So the gradient norm is non-zero. So if you take the square gradient norm, then this is a strictly positive value. So if you're not optimal yet. And what it says here is that you will do a strict progress in every step. So now we have that the new step is strictly better than the old one. That's something we didn't have in our vanilla analysis before, where we just summed up everything and then we saw that the sum was okay, the sum was being bounded. But here we actually see that the last iterate is the best, because every iterate always gets better, gets strictly better in every step. If we use this special step size here, which is very important in the future, so whenever you have a smooth function, then you can use this constant step size here. And this lemma is called sufficient decrease, because the step size is chosen such that you get this strict decrease in the function value. And we want to prove this. How can we prove this? So here again is the statement. And the proof is extremely simple. It comes directly from the definition of the gradient step, together with this assumption that we have put, which is smoothness. Okay, so first inequality here is just smoothness. And we use smoothness for the 2 points xt and xt plus 1. So we take the quadratic, which is defined at this support point xt. So that's what we have. And otherwise, nothing has happened. We just know that we are below that value by definition. And that's all. And now the next thing we do is we actually plug in the definition of the gradient step. So now we see that, oh, we have a difference of the old iterate and the new iterate. That's interesting, because that's actually, by definition, with this step size, this is the step size xt. This is the gradient step with step size 1 over L. Or depending how you want this index to be, superscript or subscript. So that's the definition of the step. So, which is actually here. No need to rewrite it. So that's what we use in the second equality here, to say I just use the definition of the step, xt plus 1 minus xt, that's minus the gradient over L. And turns out the interesting thing now is that these two terms here become kind of the same. So the first term here becomes minus the gradient norm squared, which is very nice. So this gives us progress, right? The minus means this is a strict improvement over what we had before, so that's nice. So this is the improvement, but then we also have this other term here, which comes from this second term, the quadratic error, which is making us worse. But the good thing is this term is only half as big as the good one bringing us forward. So the final result is that yes, there is a strict improvement, but the strict improvement is only 1 over 2 L times the gradient norm square. So that's the proof of the sufficient decrease, and that has very nice consequences now. So it gives kind of these stronger gradient descent results, where, as we will see, so it's not clear yet what rate this will give us, but it's already clear that every step will be better than the previous one. So what rate can we expect? So let's try to write down a theorem which actually uses these step sizes we just saw. And now this again, so of course we do only convex differentiable, and again the minimum should exist. Now the key assumptions are only one, that the function is smooth with parameter f. So this is different from the old conversions we had, where we assumed the gradient is bounded. So there, in the previous analysis, we just used Lipschitz continuity, and here we use smoothness. So let's see if you get a different rate. Also, the step size we use is quite different. And the rate you get is much more simpler than the one before. And it's a rate for the last iterate. So it's going to tell us that the last iterate is best. And it's going to tell us that how good is it? It's actually 1 over t, which is better than 1 over square root t, which you had before. So, and also it's much simpler because there's no sums anymore and everything becomes simple. The rate is just basically L over t. That's the rate. The more iterations you do, your error goes down with 1 over t. And there is a constant, which is the initial distance squared, which is also looks quite nice. So, why is this theorem true? Let's see if you can prove that. So, when we finished the vanilla analysis in the last theorem, then this is what we had. So we summed up these inner products, and that means we got the average error on the left side, and on the right side we got sum of gradients, and we got we got the initial distance. So what can we do what can we do here? So previously, we just replaced this guy by saying it's smaller than b, and we had our slow rate, which is the old one. So now we're going to do something smarter. So now we're going to replace the gradients by using the sufficient decrease condition. So gradient norm squared, we can use that with sufficient decrease. Let's see, sorry. And here is gradient norm squared, and we can see that gradient norm squared is directly related to the difference in function values. So that's what we're going to do now. So I'm going to take gradient norm squared to the left side. I will see it's smaller than fxt minus fxt minus 1, plus 1. So that's what I'm going to do with these gradient norms here in yellow. So gradient norm, and I have the 1 over L, and that I claimed. So from here to here, this is really the sufficient decrease condition. Because that's exactly what we said, right? The difference, the progress I make is 1 over L times the gradient norm, at least. So progress is at least as good. So for us, this is all summed up when we talk about the vanilla analysis. And now if you sum up all these improvements, then only thing remains is the first function value minus the last function value, which looks good. So now we have bounded this middle term, and this will directly, so if you plug it in, you will see that this is the only thing which survives, and you will see that this proves the theorem that we had, so that the final rate you get is going to be 1 over t. And this, how you can see that, so the proof is not finished here yet, so this is not true here. So what we still need to do is to plug everything together to see if you can get the 1 over t rate. So how do you get this? So now where we are at the moment is that the thing here is upper bounded by this term here plus the initial function value. So that's what we have now, and let's write this down all together. So and also I will plug in the step size gamma. So here you can see there's still some step sizes remaining. It's gamma here and here. So I'll plug in the 1 over L here and see what remains from the vanilla analysis. So on the left side I will do nothing, and on the right side I will plug in what we just said. So that's what remains here, nothing on the left side. Here the sum stuff is, so this here is sufficient decrease, what we just discussed. And then on the right side, what has happened? Nothing. I just plugged in the step size. So that term here kind of remains. So there's nothing I do with it. So okay, but this now looks interesting. So now we have these guys on the right minus the sum of the function differences. If I rewrite this, so I'll just take the last integer also to the left side, then I get the sum from 1 to t of my function values, and that is bounded then by the initial distance. And now I'm really done with the rate. So because now I have that the sum of my errors is small, so that also get that the average of my errors is small. But that also means that the last error is small. So and why is the last error better than the previous ones? So why is the last error better than the average error? That's because every error becomes smaller than the previous one, right? We said that also follows directly from sufficient decrease, that every error is better than the previous one. Therefore, it's better than the average one. And the average one, we just had that on our previous equation. We just saw that this is the final rate we get. So now everything is divided by t, and we are done. We have our final rate. And now I can say that the proof is finished, actually. So, okay, this is the final rate. So what we saw is that the error is smaller than 1 over t. That was what the theorem gave. If you wanna reformulate it again, you say you don't care about t, you want to get an epsilon error. If you want to get an epsilon error, then I can tell you, again, very simple, I just solve for t. If your t is at least 1 over epsilon times the squared initial distance times L, then you're good enough, then you have an epsilon error. So if we compare this a bit to what we had in the previous example, then we saw in the example actually I showed you, then maybe you want to reach an error of 0.01. So, and now in our case, how long does that take? So let's say that's our epsilon. How long does that take? Well, it takes r squared L over epsilon. So that's r squared L times 50. Sounds good so far. And in the previous case, this was much more, right? So this was actually 1 over epsilon squared. In the previous case, where we only assumed the Lipschitz continuity. So this is much faster. So much faster than the old condition one. So if you're smooth, then 1 over epsilon steps are enough, That's much faster than the 1 over epsilon squared steps we had before. Also, what's kind of nice here is that there is only one parameter we need to know to run this algorithm. Previously, you need to know both the R and the B, which is a bit tricky. So now we only need to know one parameter L. And if you know this L or not, that again, there is a trick you can do. So you can do kind of a binary search if you don't know it, or you can think about what to do, how to detect if your L is too big or too small. So there is a way you can deal if you don't know L. And then, so L is really the only thing you need to know to run this algorithm, because this is giving you your step size. You don't even need to know like how many steps you want to run. You just need to know the L, and then you can run as long as you want. You can stop anytime, and you will always have the result for the current iterate. So whenever you stop, you have this result. It's not just for the average of the iterates. So that's a strong result, and it's faster than the one before. And we've already seen some functions which are smooth, so that's nice, but we also seen that, okay, some functions, sometimes they can have either property, sometimes they're only continuous and not smooth, and sometimes they're smooth. So it depends on what you optimize to see which rate you can have. And on the next week, actually, we're gonna talk about an even faster conversion, so actually which is exponentially faster if we have another small assumption we need to impose on our function f. And then see you next week.